I am David, Assistant Professor, Department of Mechanical Engineering, Roguni College of Engineering and Technology. In this video, I am going to teach additive manufacturing from Unit 2, Design for Additive Manufacturing. This is considered as Model 2, that is Material Classification. So these are the materials we are using in additive manufacturing. It is polymers, metals, ceramics, composites. Polymers are divided into ABS polymer, acrylics, cellulose, nylon, polycarbonate, thermoplastic polyester, polyethylene, polypropylene, polyvinyl chloride. These are the thermal characteristics of the materials. It is x-axis, it is considered as temperature, y-axis specific volume. These are the increase or decrease specific volume with the increase of temperature. It shows. These are the load displacement characteristics of metals and polymers. So it's just like a stress strain diagram. The metals are characterized by a linear elastic region followed by a non-linear plastic region. Polymers generally brittle at temperatures much lower than Tg, but their ductility increases as temperature rises. As the temperature increases to levels above Tg, a peak load is reached and a neck begins to form. As a specimen approaches its fracture point, the load rises due to the stretching of molecules. These are the material classifications. It is laser additive manufacturing of metallic components. It is divided into partial melting powder, completely melting powder. It is again laser sintering process, pre-spreading of powder before using scanning, then multi-component metals and Xi2 MMC. And in this side, complete melting of powder, that is laser melting deposition, pre-spreading of powder before laser scanning, coaxial powder feeding with synchronized laser scanning, pure metal powders, alloy powders, Xi2 and Ni2 MMCs are coming under here. Metals are pure metals, that is Ti, titanium, Ca, copper, gold, silver. These are the coming under pure metals. Alloys, Ti based, Na based, Fe based, Al based, PCO based, Co based materials are available. Material process consideration and control methods. Absorptions. Processes of AM generally involve a direct interaction of powders with laser beam. The determination of absorbance of powders is particularly important to thermal development because it allows one to determine the suitable processing window. Free of a non-response of powder due to insufficient laser energy input or a pronounced material evaporation due to an excessive energy input. Surface tension and wettability. The liquid-solid wetting characteristics are crucial for successful AM process. The wetting behavior of a partially metalled LS system involves the wetting between structural metal and liquid binder as well as the wetting between structural and molten system and the solidified pre-processed layer. For the completely melted LMLMT system, the second kind of wetting behavior prevails. Viscosity an important property. Besides the favorable wettability, it is required that the viscosity of the melt is low enough such that it is successfully spreads on the previously processed layer, and in case of LS, surrounds the solid structural particles. For a LS system consisting of a solid liquid mixture, the viscosity of molten material mu is expressed as in this equation. Ceramics. Additive manufacturing technology has been successfully demonstrated its advantage in producing ceramic parts through both direct and indirect methods. In direct methods, this process typically creates a ceramic green body with a high content of organic or inorganic binders. Then binder burnout and densification of the green body are conducted in a conventional sintering step. A fuel injector structure of aircraft engine, aluminum and silica cores, and shells for investing casting, graphite bipolar plates for fuel cells, and bioceramic bone scaffolds were fabricated using SLS by laser sintering the mixture of ceramic powder and binder, and then removing the binder and sintering the parts in a furnace. So these are the direct method. It is direct fabrication of ceramic parts using AM process in much more challenging due to the high melting temperatures of ceramics such as aluminum chloride oxide, and also large thermal gradients, thermal stresses and residue stress associated with the melting resolidifying in the laser based AM processes. Example, SLM process was investigated to fabricate ceramic parts from a mixture of zirconia and alumina by completely melting the ceramic powder. The ceramic powder bed was preheated to a temperature higher than 1600 degrees Celsius to reduce thermal stresses, and nearly fully dense, crack-free parts were obtained without any post-processing. So these are the materials which is composed one with another. That is composites. Okay, thank you.